Okay, so J.J. Thomson had already kind of determined the charge to mass ratio of an electron by using a cathode ray tube. He'd done experiments with that, looking at the angle of deflection when brought into an electric field and a magnetic field. We'll get more into magnetic fields in chapter 12. Okay, but that had been done. And so we knew the charge to mass ratio of an electron. The problem was we didn't know the charge or the mass. We just knew the ratio between them, right? But we didn't actually have numbers for them. So Robert Millikan came along and he actually figured out a way to determine what is the charge of an electron. And as we know, the charge of the electron is often called the elementary charge. Okay, and so that is the base kind of unit of charge. You can have E, you can have 2E, you can have 3E, but you can never have 1/2 of E or 3/2 of E, right? You must have integer multiples of E. You can also have the negative values of those, but just remember that doesn't denote anything other than the fact that it's the opposite it has the opposite characteristics as positive charge, so that they attract or repel based on what kind of other charges they're near. So just to give you a kind of a visual of how Millikan did this, I'll show you a quick video, okay? A quick video of someone with just helps to get a visual of it. And then we'll come back and we'll look at more depth at the kind of math and the, well, the mechanics involved.
In a series of experiments carried out between 1908 and 1917, R. A. Millikan succeeded in measuring the charge of the electron with great precision. In his experiment, a fine mist of oil was sprayed into the upper chamber with an atomizer. Some of the tiny oil droplets fell through the hole in the upper floor, and Millikan was able to determine the mass of an oil drop from its terminal velocity. Next, Millikan used an X-ray source to ionize gas molecules in the chamber. Electrons from this ionization process adhere to the oil droplets. The oil droplets now carry a negative charge. The negatively charged oil droplets can be halted by adjusting the voltage across the two plates. As the voltage across the plates is increased, the velocity of the oil drops slows. As the voltage is increased further, some drops will begin to move upward toward the positive plate. If the voltage is set just right, an oil drop can be suspended. When an oil drop is suspended, its weight, mass times acceleration due to gravity, is exactly counterbalanced by the electric force applied. The electric force applied equals the applied electric field, E, times the charge on the drop, Q. Since the mass of the oil drop, the acceleration due to gravity, and the applied electric field are known, Millikan could solve for Q, which is the charge on the drop. Millikan found that droplets had different charges, but each was a whole number multiple of a smaller charge, equal to negative 1.60 times 10 to the negative 19th coulombs. Millikan concluded that this was the fundamental unit of charge, the charge of an electron. From the charge of an electron and the charge-to-mass ratio of an electron determined by Thomson using a cathode ray tube, Millikan was able to calculate the mass of an electron. The mass of an electron, 9.10 times 10 to the negative 28th grams, is an exceedingly small mass.
Okay, so essentially, uh, Millikan sprayed some oil drops, right, into this this electric field here between these two oppositely charged plates. And because he kind of knew the density of the oil he was working with, he could see on his microscope the size of the oil, right? He could very easily work out the mass of a drop, right? If you know the density and you know the volume, you can work out the mass because density is just mass per volume, right? Um, so once these were charged, he had kind of X-rays coming in that would ionize the air, and then these would pick up a negative charge, okay? He used the electric force upward, and he balanced it with the gravitational force downward, right? If there was no electric field here, what would these oil drops do? They would eventually just kind of fall down, right? So he got those to balance since he knew the mass, right? Or sorry, since he knew the force of gravity and the electric force, electrostatic force were balanced, he was able to work out what the charge and the mass were. We'll work on that in a second here. Okay. First, let's just kind of get a feel for it. What is it that's going on here? Okay, let's look at these free body diagrams because it's a good way to kind of wrap your head around what this experiment is actually all about. Okay, so a little bit of a refresher on free body diagrams. We've done a few, but we haven't really dove into them since physics 20. Okay, so stationary. Would it, whoops, what would it look like if a oil drop was stationary? So if it was in this electric field and it was stationary, well, if it's stationary, it's not accelerating. Remember, that's what we need to be really focused on when we're looking at free body diagrams and on in dynamics in general, right? Is it accelerating? That's what we really care about. Is it moving is an important question to answer, but when it comes to dynamics, what really matters is not is it moving, is it is accelerating. Okay, so if it's stationary, not only is it not accelerating, it's not even moving. So all forces must be balanced, right? So in the case of a stationary drop, which was the kind of the most important to Millikan's experiment, the electric force, the electrostatic force upward was equal but opposite to the gravitational force downwards. Okay, and so that's what that would look like as a free body. If it's moving up at 3 meters per second, right, don't make the mistake of saying that the force electric would be larger up, because it wouldn't. It's not accelerating up. The forces aren't unbalanced up. It's just moving up. So it would actually, right, is it accelerating? No. So there's no net force. So whatever electrostatic force there is up, there must be an equal and opposite force of gravity down. Okay, if we look now at C, now it's accelerating up. So to accelerate, what is required? A net force, right? Something cannot accelerate unless there's a net force present. So we have our force of gravity, and then what do we know? If it's accelerating up, there needs to be a net force up, right? So our electrostatic force must be bigger than our force of gravity. Okay, maybe should have drawn that a little bit more obvious, but if we look at our VAD, right, there's FE, there's FG, a little bit smaller. And so what's the net force? Well, it goes from the beginning of our first vector to the end of our last. So that overall it does accelerate up. Okay, we look at D, accelerating down at 3 meters per second squared. Well, it should look similar, except this same size F net will be down. Okay, assuming the mass of the oil drop is the same here, which we kind of have been assuming. Okay, so now the force of gravity, I guess, kind of hasn't changed because we're assuming the same mass of the oil drop this entire time. However, the electrostatic force must be smaller, so that if we were to draw a VAD, right, we would end up with this, but kind of the mirror image where the larger vector is the one pointed down and the smaller vector is the one pointed up, and then we would switch the labels so that F net is same size-ish, but down, okay? Not same size-ish in theory, just I'm saying in our imperfect drawing. Okay, in E, accelerating down at 9.81 meters per second squared. So if something is accelerating down at 9.81 meters per second squared, what force is acting on it? Okay, the force of gravity. And what other forces? Well, nothing, right? If it's accelerating downward at 9.81 meters per second squared, that is free fall. Okay, so it's accelerating downward at 9.81 meters per second squared. Unless I gave you some really weird example where there was some other upward force and then some other downward force that cancel each other out, right? But don't overthink it. In the case of Millikan's oil drop, it's just saying we haven't applied an electric force. We haven't made an electric field. We haven't charged the plates. They're neutral. And so the oil drops are essentially in free fall. Now, what if it's accelerating down at 12 meters per second squared? Well, then we've actually must have given we've not only are we in free fall, something else is acting downward to make it even accelerate down more quickly than it would in free fall. It's falling faster than gravity would pull it downward on its own. So imagine these drops, right? We said we kind of gave them a negative charge, or at least the ones that we were able to suspend, we gave a negative charge. But you can imagine some might have picked up a positive charge as we ionize the air. So some of them, in theory, could have ended up not being pulled back upward by the electric field, but instead accelerated down even more quickly than gravity would have taken them down. And so what would that look like? Well, we would have our simplified diagram, the free body diagram. And yep, as always, the force of gravity. And now what direction would the electrostatic force be in? It would also be down. And if we were to draw a VAD, right, we would have them tip to tail, FG, FE, so that F net down is even bigger. And that's how we would get a larger downward acceleration by A equals F net over M. Okay, so great. We talked about how Millikan could do this. He was able to determine the charge of the electron, but let's actually kind of recreate what Millikan did, right? See if we can put ourselves in his mind frame. So we're going to focus on our A free body diagram, right? Because this is really what Millikan tried to achieve. He tried to achieve a suspended oil drop where the electric force was certainly equal to the gravitational force downwards, okay? Technically B would also work, but you got to remember we're working with our eyes here, right? So it can be difficult to tell, is something really in uniform motion? Is it accelerating slightly, just a little bit, right? So it's kind of easier to work with something that is for sure stationary, okay? So derive the equation that would be used to determine the charge on the drop if it were suspended. Well, if it's suspended, what do we know about its motion, okay? Well, it's not moving, you're right, so V certainly does equal 0, but more importantly, when we're talking about forces, the acceleration equals 0, okay? And if the acceleration is 0, then we know F net equals 0. As always, what does F net mean? It means add up all the forces acting on it. Okay, so we have F net being Fe plus Fg, and those must equal 0, okay? Now Fe, what's the equation for that? Well, the useful one here is going to be, I'm just going to write it off to the side so you can see where it's coming from as it looks on your formula sheet, right? Electric field is equal to the electrostatic force over the charge, or newtons per coulomb. And so when I rearrange that for Fe, I get EQ, okay, plus Fg, as we know from physics 20, plus Mg equals 0. Now that's all well and good, but if we go back to our picture, right, were we given the electric field strength, or was it kind of implied that that was a known value? Not really, right? So yes, it is a straightforward calculation, but we got to think kind of in terms, whenever you're asked to derive an equation, you should kind of always make sure that all variables are either mentioned as usable or that you could measure them from the setup you're given, okay? So what can I measure from the setup I'm given? Well, I could get electric field, right? Electric field is equal to the potential difference over the plate separation. Well, those are very easily measurable values, right? Millikan could very easily see on the voltmeter what voltage was existing between his plates, and he could obviously very easily measure or even set the separation distance he wanted between those plates. So let's just plug that now in there for that. So we have that the potential difference over the plate separation distance times the charge. Remember, what are we doing here? We're trying to find the charge. This was Millikan's goal. So we knew the charge to mass ratio from Thomson's experiment, but now we need to know, well, what is the charge? Okay. So then let's isolate this for Q. We'll just subtract mg, the gravitational force, from both sides. Now we have the potential difference over this plate separation distance times the charge equals negative mg, and multiply both sides by the reciprocal of this to get Q all alone. So that's separation distance over voltage, right? If I multiply that by that, then those are going to cancel out, and those are going to cancel out. And so on this side, if I do the same, times the separation distance over the potential difference, and there we go. This is what Millikan arrived at as well. I'm actually just gonna, if we multiply by the separation distance divided by the potential difference, that's what we get. Okay, now when Millikan did this, as it said in the video, he did this calculation a whole bunch of times. He did it over and over and over and over and over and over and over, right? Mass was easily determinable from the experiment, knowing the density of the oil, knowing the size of the drop, okay? Acceleration due to Earth on gravity, well, we know that. We know very easily the separation distance between the plates, and we measured the voltage using the voltmeter attached to the system. And so he repeated this over and over and over again, and he did get different charges. He was expecting to get different charges because he knew not every oil drop was exactly the same. He was doing it sometimes at lower voltages to get it to balance, sometimes at higher voltages. But what he did notice is that every time it was a multiple of 1.6 times 10 to the negative 19 coulombs. That was always the charge on the oil drop. Now, careful what I said there. It wasn't always 1.6 times 10 to the negative 19 coulombs. That wasn't always the charge, but it was always a multiple of that charge. So you might see 3.2 times 10 to the negative 19 coulombs. Okay. You might see 4.8 times 10 to the negative 19 coulombs on the drop. Okay. Millikan might have seen 6.4 times 10 to the negative 19 coulombs. Okay, you see where I'm going with this. It was always a multiple, though, of this. He never saw half of this. He never saw 0.8 times 10 to the negative 19 coulombs. It was always a multiple of this, right? So we might say it was n, where n is an integer, times 1.6 times 10 to the negative 19 coulombs. And so he reasoned that if something had, for example, one excess electron, it would have this charge. If it had two excess electrons, it would have this charge. If it had three excess electrons, it would have this charge. Four. But something cannot have half of an excess electron, and that's why we reasoned that that is the charge of an electron. Okay, taking that value and going back to the charge to mass ratio that Thomson had worked out, he was also able to get the mass of an electron.